Welcome back. We're going to look at waves in this video. I've gone ahead and filled everything in advance so we can just talk about it as we're looking at the diagrams. A transverse wave is this one that is the classic wave shape, that up and down. It consists of crests and troughs, the high and the low points, a wavelength measured between crest to crest, or you could do trough to trough, an amplitude, which is how high you go from rest to crest, and there's technically also something called wave height. I highly doubt you would see that. It's where you go from the trough to the crest, and that would be typically how you measure, say, a surface wave in the ocean instead of the amplitude, because it's more convenient to measure the displacement from the trough as you ride up to the crest and measure the height of the wave. But the energy determining part of the wave is actually the amplitude, and we did that with our little door handle demonstration. A whole bunch of little waves with very small amplitudes could not open up the door handle, but a single wave with a very large amplitude carried sufficient energy at one time to the doorknob to actually open it and pull the door open. And that's how you can tell that amplitude is what determines the energy content of this wave. Alright, and technically also there is one other thing on here. These would represent nodes, especially in a standing wave. If I had another wave going through like this represents a node, a point where the wave is not actually moving the medium. Okay. And we saw those when we did the spring, and we got this wave shape, this really big wave, and it just kept alternating between up and down in these two positions. And you could see that the middle part never really seemed to be changing. It was always staying in the same place. That's the node, where there is no movement of the medium. Alright, a longitudinal wave is another way to carry energy, and it is a compression and rarefaction chain. So compressions are where you squeeze them together, rarefactions are where you pull them apart. Sound waves are the classic example of a longitudinal wave, because a speaker membrane actually works just by pushing back and forth. Let me zoom out so you can see this. Just pushing a membrane back and forth, in and out. So if you took a sheet of paper, you can actually make sound by moving it forwards and backwards, because it's actually pushing air in and out, in and out, in and out. Printer paper is a pretty terrible paper to do that with, incidentally, because it's so thin. Try it with something thicker and you'll hear exactly what I'm talking about. Or if any of you have a subwoofer, you can crank that up and put some low frequency sounds through it, and you'll see it's actually bending out and then pulling back in. And every time it pushes out, it compresses the air in front of it, making that sound wave, that compression wave that you actually hear. The thicker the compressions, so the longer those are, the bigger the amplitude, or the more energy that wave will carry. Alright, mechanical waves have to travel through some sort of medium. They can't just go through empty space, so there is no sound wave in space because there are no air particles to compress and rarefact. They can't stretch and compress in space because there's not anything there. Now, that doesn't mean energy cannot move through space. Electromagnetic waves, which look like two transverse waves, one of them going in this direction and the other one going in this direction, and they just sort of fishtail across space, bouncing off of each other's fields, don't require a medium. That's how energy can get from the sun to the earth. Even though there's nothing in between us to carry that energy, electromagnetic waves are perfectly capable of propagating without the help of a medium. In fact, a medium slows them down. Alright. Shaking a rope, that's a transverse wave. Slinky, assuming you're doing it back and forth like we did in class, is a compression or longitudinal wave. Of course, if you did the slinky up and down, you would wind up generating a transverse wave, in which the energy is going this way, but the medium is just going this way. Mechanical waves are broken down into our transverse and longitudinal waves. There's also surface waves that you would see in the ocean, and they just sort of move things in a circular path. But ultimately there is no displacement because everything's just moving in these series of circles. But by far the most important, transverse and longitudinal. Surface waves, not terribly important for your test. Alright, we already went through these different parts, so I'll just scooch down. When two or more waves combine to form a greater amplitude, that is constructive interference. That's in the note handout that I gave you. And we attempted to make some of this on the spring. We were marginally successful. It was just very hard to see in real time with such a small spring. And by small, I mean the size of the room. If you took this wave, let's not make it an entire wave, just a pulse, and cross it with... Oops, we want to do constructive interference here. This wave, then when they meet in the middle, you'll wind up with a wave that has twice the amplitude. Now the opposite is destructive, which is what I started to draw there. The waves are traveling in opposite directions, have opposite amplitudes. When they meet in the middle, nothing is going to happen. In fact, it's going to appear to go totally flat as the waves pass through each other, and this wave tries to pull up while this wave tries to pull down by the same amount, and absolutely nothing is visible at that point. But then they'll reappear on opposite sides, traveling in their original direction, because waves just pass through each other, because it's nothing physical, it's just a bunch of energy that's moving through something. And that energy can just pass through other energy without itself being affected. Okay, tune in for the next video to do electricity. I don't want to slap it onto this video and make it too long.